Any questions?
I have a question. Are the outputs from the network actions now, or the Q table from previous?
So before we have like this Q of S,
Right.
and it returns like whatever, some list of values for each action, right? 10 minus 100, right?
This is the rewards for this action, right?
Yeah, this is like the value, right? The value function.
Right.
It's kind of like how good is this? The state for each action.
So the output from my network would be something like that one value.
Yeah. So the output is gonna be the input is gonna be the state, and the output gonna be an array of the size of actions.
But these actions are for one state, not for multiple states, right?
So we let the neural network decide. So the input is the state, right?
Right.
And the state can be continuous, the state can be discrete. So the input is just the state, right? And depending on the input features or the input values, certain neurons are activated. And depending on this, it's gonna generate a certain output, right? So now we just have a Q table, right? But if I have, say, a continuous problem, right? I have indefinitely many, like infinite many states, right? You cannot make it in a table, right? Or you have like a giant game, and then you cannot put it in a state. But the state can be very small, and just let the neural network decide what the action is.
So it basically maps the state to the reward, the value function. Basically, state and action pairs to the value function. And the way that it does it, it takes the state and gives you an array of size, your action size, basically, how many actions.
So basically,
and then basically for each action, those are the value functions. So for each state, you have an array of size, action size, right? And then each of the actions has values.
Could I interpret the number of those actions as a reward of getting into the state?
No.
So basically, you interpret it as like which action is better. Like if I take this action, the value of that action is not value, basically.
Oh.
It's the value function.
You call it favorable, right?
Yeah, it's a state action value function. So neural networks are universal function approximators. So if you give him a neural network, if you give him enough data, that's what the input is, and that's what the output is, it will kind of approximate the function. And the function we want to approximate here is the state value function for the state action pairs, right? And the input is the state, and the output is like the state action value function for each kind of action.
I think another thing is like maybe if your actions are not just like discrete, right? If you don't have like 5 separate actions, your action is like a continuous value, right?
Yeah.
Like as an input to something, let's say, right? Let's say how much you accelerate in a car, right? Then it could be designed different way. So basically, it takes action and state as an input, and then gives you the value. But in this case, since the actions are limited numbers, right? It just takes the state and it gives you an array of
predefined actions.
Yeah, exactly.
So would I be correct in saying that once it goes through one transaction, that will be called as that transition that we talked about, and then once we have a couple of them, then we decide backpropagation?
So you play 100 episodes, right? You take from this 100 episodes, you make 100 transition, 100 steps. So you have 100 states. You experience 100 states. And you sample 32 of these states. So you take these 32 states, you make a batch out of it, right? And you push it through the neural network, you make the forward propagation. And then you calculate for each state, you kind of calculate the TD error, right? And then you take the average of this TD error, this is the loss of the forward pass, and you backpropagate it.
I think like it's important to kind of like from the previous exercise that we had the table for Q. Now we have a neural network for the Q. So the problem is that if you have like huge number of states, you can't store all the values. And by the way, like you can't do like experiments for all the states. You may not pass all of them. You kind of generalize. You have some states, values for some states, and then you use the machine learning or neural network to generalize that idea. So let's say if you have some state you have never experienced, but you have a good estimation for that because you have visited nearby states because you generalize from that. Say if the value function for this state is this, for the neighborhood, it's going to be this, right?
So in each sample, you're learning the best greedy action. You're not learning anything about.
No, you're not learning the best greedy action.
When each state, there were multiple actions that you could have taken.
Yes.
So you're not learning about all possible actions. You're only learning about some subset of those actions.
So the reason you take the greedy is because you're kind of off policy, right? So this has kind of have to do, how do I estimate the value function, right? You can be on policy, which means I get my value function for all the states. I treat them like as a kind of, I divide it by the whole value of it. So I sum it up, divide it. So, and then I sample from it, right? Or I sample whatever, epsilon greedy or whatever. Sample from it. Then I'm on policy, right? And then you take this action, which would be like the action your agent would be taking, right? So you're on the policy of the agent. But you can also do it off policy, right? And you just take the maximum value, take the action with the maximum value, and you use this one. And this is just like a different way how you estimate the value function. This has more to do if you do on policy or off policy. But pretty much everything is off policy.
So I think what you're saying is like you take one action and you don't take the other possible actions, right?
You're ignoring them.
Yeah. So basically what you do, the whole thing is that if you always take one action, you would never learn about other actions in that state. But what you do, the epsilon thing helps here, right? So you take some random actions sometimes. So that's why you try all of them. But there's a trade-off, right? I mean, how many times you should take some action to make sure that what's going to give it to you? Because also there's like a uncertainty where that action is going to take you. Because sometimes the environment is not deterministic. Taking the same action 2 times, it's going to take you to 2 different places.
All right, let's move on.
Any other questions?
So, sorry, I just want to ask one quick question. The way that the neural network is picking up previous states is when I pass the forward pass the previous state, right? So it doesn't have any information about states like 1 and 0 finding state 5.
No, it doesn't. It doesn't take information from previous state. Just the current state and the next state.
Oh, okay.
So yeah, we talked a little bit about this last time too.
Okay, sorry.
So just take a minute. Just following up from this question was what I understood earlier was there were 100 states, we sampled 30 of them, right?
Yeah.
So we run through them. This becomes our input dimensions. I'm just wondering that on each node, would the output dimensions be the number of actions it can take from each node? Would that be the idea?
So the input of the neural network is like one state.
One state, right?
Yeah.
And the
So if you have a batch, you sample 32 times. You just run 32 data points through it.
Yeah, that
So
is-
you make 32 predictions, right?
Yeah.
So for each state, you predict all the action values, all the values for each action.
So that's what I'm saying, that if the input layer were to do that particular thing which has, say for state 1, if I could do 10 actions,
Yeah.
would I go through all 10 or would I not do that?
Well, so what you do, you go through your transition, right? You know the action you have taken, right? So you take your state, you predict your actions, right? Then you take the value of the action you have taken, right? So we have a very specific action you've taken. So for each data point, you take the action you have taken. This is this value. This is this value. And then you take the same array for the pure vanilla one, where you don't have 2 models. You take the same prediction, you take the maximum, the max possible. And this is this value. And you multiply it with gamma plus the reward. And then this is YE. And then this is for your error calculation. And this is like how you do it with convolutional. So you just redefine the input and the output stuff. We're gonna just skip it for now. And what I did here is because you have the same agent and you have always different neural networks you want to implement it or you want to run it on. So what I did, I built like a factory pattern for initializing the neural networks you want to do. You want to run it through. And the way I do it, I have like I define some enum, and these are like basically the different neural network types we want to run through. And then we say a factory, and the factory can register a constructor, and the register constructor is nothing else. You take the enum as a key, and you return like the class constructor. And that's it. And now we're gonna go to the deep Q agent part. So there's some part for you to code, and we're gonna have like a quick question. So we can just skip the coding part, and I just show you the results, or then I can show you a little bit more about the downstream enhancements. But I think they are pretty some of them are tricky, but the one that are tricky, I don't think we will get there anyway. And it's just what's the preference. So who wants to do the coding part? No one?
Don't be shy, guys.
Give it a try, I guess.
Okay, yeah, okay, then we just don't do the coding part then.